criticize.
So how are things in Warwick, Józef? Huh?
All right, super busy. I'm just straight coming from teaching, so
In the
I
afternoon?
finished 5 minutes ago.
Huh?
I finished 5 minutes ago teaching, so
The afternoon you're
straight
teaching?
from a lecture.
Yeah. Oh, you have classes in the late afternoon.
Yeah,
I mean, it's 5 o'clock for you or 4 o'clock, right?
yeah. So from 3 to 4.
Mm,
Sometimes I have even at 5.
I see.
So very busy, but
We still, you know, I'm still doing 10 and 11 o'clock in the morning.
I'm sure students liked it.
Well, they show, yeah, I mean, it was 560 and 561. I'm doing 561 right now, but 560, we had 70 students, you know.
It's a good number. Do they come to the lectures?
Yeah, no, it was pretty well populated. Okay. There he is. Okay. Alex is joining us this morning.
Yeah. I'll have to disappoint Alex. I'm not going to be singing or dancing.
Hi, Józef.
Hi.
I remember the University of Warwick is, for me, the association from years ago is a very good friend named Ray Dupree. Although
Yeah.
Ray was in
2 doors down.
He was he came on, so he spent a year sabbatical with me. Very smart guy, also very long sideburns. That's what I recall.
Still there.
Still, sideburns are still there, but he's probably shrinking, huh?
Well, but he's actually, he's very much into plants now. So I don't know if you ever seen, he got a series of really nice papers on isotopically labeled plants.
Yeah, he sends me stuff. He came, I mean, this was in the early days of solid state NMR when there were just very few places that were doing it at all. And he just wanted to come and learn all the techniques. And I remember we went to a conference in Turkey together. It was wonderful with his wife. And so anyway, please give him my warmest regards when you see him, Józef.
I shall.
And no singing and dancing from you, and no singing from me, I'm afraid. No.
Yeah. And yeah, he's also not traveling anywhere. Obviously, none of us are traveling, right? So,
but for different reasons, I guess.
Exactly.
Different reasons. No, when he was here, he traveled a lot. He learned a lot. I mean, he really picked up a huge amount of stuff and really brought it to Warwick. Mostly material science, physics, and so on. So plants were one of the things that always in the back of his mind. Interesting, yeah. I guess as we get older, we all become closer to vegetables, huh, Bob?
I'm not. No, I'm still.
Maybe you're a carrot.
Still
Okay.
protein. Still
You're not
protein.
a cabbage. Maybe you're one of the fresh ones, like a red pepper or a carrot.
Tofu protein, right?
Right, you were always close to vegetables, Bob.
Okay. So we generally start 5 after the hour. It's when MIT classes start, Józef, if you recall, right?
A long time ago.
Alex might recall even that classes 5 past, right?
Yeah, we do 10 past. Why? They're called. So
Many places do.
give 5 minutes for transitions.
We have 10 minutes for transitions.
Oh, so it's up to 55. That's X55 and then X1, X plus 1, 05.
Yeah.
I see. All right. So we move it to, and it's very confusing because when you have a seminar or you have a faculty meeting, unless they specify, people do not know whether to show up at 8 o'clock or 8:10.
Yeah.
And always half of them show up, another half don't show up, and they never think, listen, be clear about what time the fucking thing starts. So it's an issue.
Yeah.
Berkeley people are not as smart as MIT people, and MIT people can just
Well, no, it's
evidence and just deduce it right away, obviously.
It's mostly, it's all in one building, when it's inside. So for the most part, so that makes it easier to go from one class to another. I mean, there are exceptions to that, you know.
It's still number 6. Building is the building still called number 6?
6, 18, 56, 16. Yeah. Mhm.
They're all connected, yeah. So I
Yeah.
remember 6 because our entrance had a back entrance directly from Memorial Drive
Down to the basement of building 2.
right into our lab. And when I got to Berkeley from MIT, the first thing that met me was a letter with a hand on top like this that said the Justice Department is seeking you out for $400 of unpaid parking citations on Memorial Drive. Because I just come there any time of day. I'd park next to them and just going through the snowing or whatever, going to the lab at any time of day, and I just parked there. So $400. Anyway, I went to the trial. I figured, what can I lose? And I said to the judge, he said, "How do you plead?" I said, "Excuse me, Your Honor, for this kind of crime, can I plead temporary insanity?" And he said, "Never heard that one before. Okay, $100 and you're out of here." So,
Okay, all right. With that introduction, I suppose we should introduce the speakers today, right? And the first one is Nino Wili, I guess, from the ETH in Zurich. And Nino is a PhD student. Are you? Maybe you've graduated already. I don't know.
I just finished. Yeah, I just finished.
Just finishing. And he's officially an EPR spectroscopist, but he's been dabbling very nicely into some very interesting DNP experiments, which he's going to tell us about today. And the second speaker is Józef Lewandowski, and I will describe his background when we get to him in about 20 or 30 minutes. Okay, so Nino, why don't you go on?
Let me share my screen. Oops. Get this all in place. Okay. You see my pointer? Everything okay? Good. Yep. Okay. So I'm going to talk about DNP and reverse DNP. And so as an EPR spectroscopist, I think in terms of chemistry, what I always found most interesting are actually electron-nuclear interactions. Because they kind of tell you where the electron resides and what the electronic structure is. And of course, the hyperfine couplings are also central to DNP. And this is a little bit how I got into this. And then the second part, I will then also talk a little bit about this reverse DNP. But first, I just want to talk about some experiments in low field DNP. So this was in collaboration with Kong and Anders Nielsen and Aarhus. So this was a pandemic collaboration basically over Zoom. But I did all the experiments at ETH Zurich. And I had a lot of help also from Matthias Ernst about the theory. So the spectrometer that I use is basically, it's an EPR spectrometer and quite low field. So it's 0.35 Tesla, corresponding to 9.5 gigahertz and 15 megahertz proton frequency. We have a high power amplifier. With this spectrometer, we can do electron excitation and detection. The second part for the NMR is basically a very cheap NMR spectrometer for proton excitation and detection. They're both connected to a probe head, which is a microwave resonator, which allows us about 40 megahertz electron rotation frequency. And it also has a tuned NMR coil, so we can do NMR detection. And then basically, I just interfaced this with an Arduino to count how many EPR triggers I had. Because in these pulse DNP experiments, what you do, you have a DNP step, then you detect the NMR signal, but usually you repeat this DNP step thousands of times because you only have a few millimolar electrons, but basically you want to polarize the whole sample. And for this, I just use an Arduino with a, I guess, better NMR spectrometer. You could just implement it in the spectrometer. So both of them were more or less home built. One of them, this was built by Daniel Klose and René Chakalar in our group. And the interfacing with the NMR I did myself with the master student, Laura Völker, which did some brilliant work on this. The sample I used was just this OXO or OXO 63 that I got as a gift from Jan Hendrik in Copenhagen. used this in DNP juice, just the typical formulation of glycerol, deuterated glycerol, deuterated water, and 10% of water. Concentration of 5 millimole and ATK. And these conditions are mostly because some older papers of Bob also use this formulation. It's not really like optimized for, like, at least for, I didn't optimize anything myself. Let's put it like this. Now, where's this the inspiration coming from? So there was a lot of early pulse DNP work by Henstra and Wenkebach and co-workers. And then also in the last maybe decade, Bob did and his group did a lot of also low field, low frequency pulse DNP, where you can really control the electron spins. But then also in the last maybe 2-3 years, there were some papers by Kong, this top DNP. There's a paper from the NV Center community where they use basically echo sequences that are synchronized with the nuclear Larmor frequency, nuclear Zeeman frequency. And also actually in this ZOOMinar series, Jenny Mattis also described this TPPM DNP or XIX DNP. So there seems to be a lot of interest in these modulated pulse DNP sequence that take inspiration basically from solid state recoupling. Now, what I'm going to show you, there's one very important term, and this is this so-called effective field. So if you have some kind of modulated sequence like this, where you have 2 pulses with some length, opposite phases, a total length, and this is repeated several times, which gives you a modulation time and a modulation frequency, with some parameters here that don't really matter for the example. So what we do in the description, we go into an interaction frame with a microwave pulse sequence, so with these pulses, which is the usual toggling frame. But what is important is that we include the offset in this description, because the offset can actually be the biggest part. The electron offset can be the biggest interaction, basically. So we have to do this, that like average Hamiltonian or Floquet converges nicely. What this gives you is you have an electron spin, and you basically rotate that in 3D. So this, like all this interaction frame transformation is a 3-dimensional transformation, which gives you some rotation matrix. Now you can plot this, which gives you, in this case, something, so this is the XX, XY, XZ component of this rotation matrix. And the important part here for us is basically the SZ operator in the usual rotating frame, because this is what's actually in the electron nuclear Hamiltonian that takes part there. And what is important here to note is that this rotation matrix is not cyclic with the modulation frequency. So at the start and at the end, your spins are actually at another point. If you take these 3 components and plot them in 3 dimensions, you get something like this. So the blue is the trajectory, and the black points are always at the end of each cycle. And you see that if you connect these points, they're actually connected by an overall rotation, always over one cycle. Basically, this overall rotation is what we call the effective field. And this is very important later for the resonance conditions. If you don't modulate at all, the effective field is just the CW irradiation, basically, which can be tilted due to the offset. Now, in general, the resonance conditions in this Floquet descriptions, which are common and that Kong and also Cheney uses, you have these 3 frequencies: the nuclear Zeeman frequency, the modulation frequency, and an effective field. And some multiples of this should give 0. I have a slightly different approach, which was also basically used by Anders Nielsen in Aarhus. And I only show it very pictorially here. I mean, you can define this mathematically, but I don't want to bother you with this. Let's say you have a nuclear Zeeman frequency which has a certain certain value. And now basically you just cut off all the multiples of the modulation frequency. And then the rest of this I call the nuclear effective field. If you do it like this, you you can basically write an effective Hamiltonian. It's not a difficult derivation, it's just a bit long, so I don't want to show it in detail. So you get an effective Hamiltonian where you have both effective fields, the electron and the nucleus, and some coupling Hamiltonian. And now the resonance condition is just given by these two effective fields. If the sum or the difference of these match, you get a double quantum or a zero quantum transfer resonance condition. And the second part here is actually doing the transfer. We have a scaling factor, which just scales this interaction, and this scaling factor only depends on the pulse sequence. And then B is basically just a pseudo-secular part of the hyperfine interaction. And then you have either a zero quantum or a double quantum Hamiltonian that matters depending on what resonance condition you have. Now, let's do this for this XIX sequence where we have two pulses. Here the x-axis is missing, it should come later. It's the electron offset. You see we have some effective field, and in this particular example, the effective field of the nucleus is just the nuclear Zeeman frequency. And it doesn't depend on the electron offset. And then you have the electron effective field shown in red. Basically, it can never be higher as half the modulation frequency, and that's just a convention. You can always choose it like this, but there are other choices you could make. And you see the black dots here are the resonance conditions, where they are the same, or the absolute value of the two is the same. Okay. Now what this shows you is the DNP enhancement as a function of the electron offset. And somehow I have to hide. There were the meeting controls in my way, I'm sorry. So here's the electron offset. And now I show you the DNP enhancement as a function of this offset for different choices of the two pulse length. But the sum of the pulse length is actually always the same. So 9 + 9, 12 + 6, etc. in nanoseconds. And you see in red, it's just a theoretical scaling factor at the resonance position. And it's just some broadening such that you see it. You see that this very nicely fits the experimental data that we obtain. Of course, if one of the two pulses is set to 0, it's just a normal solid effect profile. And actually, these additional dots here, these are processes that involve two nuclei. And one interesting thing is that the resonance conditions is actually always pretty much at the same, they're not exactly at the same point, but they are pretty much at the same point, because the resonance condition here is driven by the offset. But here, even here, we have a resonance condition, but the scaling factor at this point is 0. That's why there is no transfer. Okay. Now, this was basically already shown that this works by Kong and also by Jenny for this XIX. Yes, sorry. Now, what you can do, you can actually do adiabatic sweeps through these resonance conditions. So let's go back to this Hamiltonian that we had before. In the solid effect or the novel DNP or off resonance DNP, there's no modulation. So the effective field of the nucleus is just the nuclear Zeeman frequency. And your effective field on the electron is given by this known expression, so the Rabi frequency and the offset. And you just have the vector sum, basically the absolute value of the vector. Now, if you think about something like ramped amplitude novel, which is very similar to ramped amplitude cross polarization, we actually start with your effective field a little below the resonance condition. You hit it more or less in the center, and then you're a little above the resonance condition, or the above below is arbitrary and relative. And if you look at the zero quantum subspace of this, which is very typical for if you describe also cross polarization, you have the differences basically in SZ and IZ. In this subspace, an inversion corresponds to full polarization transfer. And basically the perturbation along X is your coupling in this subspace. This you cannot really control. You can indirectly via the scaling factor, but it's not so easy to do generally. And what this does, if you go through this resonance condition, basically you start with some component along Z in the zero quantum subspace, go through resonance, and then go to minus Z, or the other way around. So this is an adiabatic inversion of the zero quantum or the double quantum subspace. Now this gets actually more interesting if you have a modulation frequency, because in this case, the effective fields also depend on the modulation parameters. So the nuclear effective field depends only on the modulation length, basically, and the electron effective field also depends on any of the sequence parameters, and this dependence is not necessarily trivial. But what you can do is, for example, something like this. So this is still XIX. It's pretty low power, and it's off resonance. And the white pulses here are all X, and they are all set to 9 nanoseconds. But now, instead of setting the gray ones all to 9 nanoseconds, we start a little bit off. So we start at 8 nanoseconds. In the center, we're at 9 nanoseconds, where we hit the resonance condition. And then we go at the end, maybe we're at 10 nanoseconds. And this is just simplified. So there would be many more and smaller steps and over many more cycles. And you can see that just changing, I mean, there's not more power or anything. So all it did is that we just modulated this a little bit. And then you see that you have kind of significantly improved the DNP transfers that you have. So this is the polarization enhancement after 2 seconds of DNP. It's a function of the offsets. The XIX I showed you before. So this is the sequence that Jenny showed. And now if you just sweep through this resonance condition, you get actually quite a better enhancement for this. And you can also do this basically with the optimized parameters, and then you see the build-up curves here. So at this field, at this concentrations, we get to about polarization enhancement of 300 with a 4 megahertz mutation frequency. So that's about a third or a little less of the novel condition. Now, just very quickly, there's another thing you can do. So before here, this was just off resonant, and we directly started with the DNP. Now we just turn this into a spin lock kind of sequence. So we do it on resonant, do it with high power, but then at the start, we need a 90-degree Y pulse. And Kong basically called this base. So it's a broadband amplitude modulated signal enhancement sequence. But you see that it's actually very similar to the XIX, just it's on resonant, and the effective field is now in the XY plane. And you can compare this to solid state NMR. There's a sequence called XIX CW Dream. And I guess it's quite a mouthful. That's why we called it base in the end here. So what I show you here is the enhancement of the 2 seconds of DNP. Also, now again, as a function of the electron offset. So this basically gives you the bandwidth of the sequence. In black is the EPR spectrum, which is quite narrow. And you see that with novel, you get a certain bandwidth of the sequence, quite a good transfer. And the bandwidth here is just given by the spin lock strength that you use. And the spin lock strength is given by the nuclear Zeeman frequency. So you cannot choose this. With the ramped amplitude version, you get a little better enhancement, but the bandwidth is actually not much better. Now with this sequence here, either in the non-adiabatic version, diabatic version, I guess, or the adiabatic one, you can use basically the full power that we have. And this is basically the reason why you also get a better bandwidth compensation here. So either nearly a factor of 3. The actual enhancement is on the order of 360 with a build-up time of 12 seconds compared to the nuclear T1, which is 36 seconds in this sample. Actually, the overall gain in this particular formulation and sample is not that much better. Also because if you see it, the bandwidth of novel is just enough to cover the whole spectrum. But of course, if you would have radicals with broader spectra, then I would expect that you actually gain more here. And it's also good if you want to fulfill the novel condition for very low frequencies, because then you can use higher power that you can just by using novel. Okay. So the second part I call reverse DNP. And I think it's quite a bad name. because and you see why. And if somebody has suggestions, I'm very open to have better ones. So some inspiration for this, and like in the last years, there was this kind of renewed interest in understanding this interplay between DNP and spin diffusion. So by Song-Yi Han, by Bob and Kong, and by Sami Shana, also by Lyndon Emsley and Brad Chmelka, and I guess many others. And of course, the topic is very, very old, and there are very old papers on this. But another thing I also thought about this is in EPR, a thing called electron nuclear double resonance, or ENDOR, versus indirect detection, which is usually used in NMR. For these established ENDOR sequences, what I would say, they always use a step called where you start from electron polarization and we go to longitudinal two-spin order. And this is then manipulated. And from this, you get something about the nuclei. But it's never really only the nuclei that get manipulated. There is one sequence called CP ENDOR by Marina Benatti, where you actually do generate nuclear polarization. So in some sense, it's a DNP sequence. But then when you do RF manipulations and the detections, you actually also go via SZ, IZ. And just true indirect detection in a very purist formulation, not that that means it's better or anything, but you would go from SZ to IZ, then you would do some manipulations on the nuclei, then you would go back to electron polarization and detect this. Now, I used another spectrometer for this. So this was 1.2 Tesla. So this is 50 megahertz proton frequency. So here you see the helium transfer line. We have a high power traveling wave tube amplifier at 35 gigahertz. This is a fast AWG that allows us to do shaped pulses in the microwave region. We have a microwave resonator inside the cryostat, which takes 1.6 millimeter tubes, about 7 microliters. And with this, we can generate about 100 megahertz electron rotation frequency. Now, another thing about this part of a DNP talk, that there is actually no NMR coil in any of the experiments following this. You could put an NMR coil in, but then you would compromise the highest power that you have here, roughly by a factor of 2. And this was built by Andrin Doll some years ago. Same sample, but now I did it in water glycerol, mainly because I already had that. And this is at much, much lower concentration, at least for most part of the rest of the talk. So just again, some basic experiments. What you can do is an echo-detected field sweep. And so just sweep the field, detect an echo at each point, and you get a line width here of about 10 megahertz. And I measured T1 row, which basically in the normal way, but we have to read out with an echo because our dead time is so long. And you see that over a period of maybe 10 microseconds, basically nothing happens. At the start here, I'm not completely sure what it is, but I think it's mostly due to phase transients actually inside the microwave resonator, and you just don't get the spins quite perfectly locked in the way that you want. You could do this longer until 40 microseconds or so, but then our amplifier cannot do longer pulses, and it pretty much looks the same until then. So now to the nuclei. Basically the same experiment, but we fix the length of this pulse and we just sweep the nutation frequency of the spin lock. Of course, if you don't have any pulse, then you don't get a lot of signal in the end. But usually then at some point, if you're roughly covering the width of the spectrum, you get a nice decent signal, which gets a little bit better with more power. But in the center here, you have a big hole. And at this hole, the nutation frequency matches the the nuclear Zeeman frequency of the protons, in this case, about 50 megahertz. Now, let's sit on this power and just increase the pulse length here. You see kind of a transient signal here, signal loss. There's some not so nice things here, which is again probably due to this phase transients and that the magnetization is not nicely locked. So one way that I did to get a little nicer curves, you can just start with the full power for like 500 nanoseconds, get rid of the nasty parts. And then after 500 nanoseconds, you basically go into the matching here. And then you see kind of a dephasing curve, which is similar to what you would see, I guess, if you would look at CP intensities on the original spin, basically. And you see that it's clearly transient behavior here. And then after a few hundred, it's like 180 nanoseconds, you have a maximum. And this is similar to what Bob's team saw with normal DNP. Now, why reverse DNP? Let's think about a sequence like this, and I go through it step by step. So at the beginning of DNP, of course, the electron polarization is much higher than the proton polarization. After the DNP step, well, probably the electron polarization is still higher, but let's say they're roughly similar, at least more similar than here. If you now saturate the electrons, basically you have no electron polarization left. So now your polarization is actually lower than the proton polarization. If you do DNP now, actually at the end here, you have a non-vanishing electron polarization, even though you're saturated, but only if the original one worked. So if you generate nuclear polarization here and you get it back, then you get electron polarization that you can detect. So in basically one sentence, if you have a coherent transfer, and DNP is a coherent transfer, it should work both ways, actually. So how does this look? Let's implement this. So DNP, saturate the electrons, do DNP again, and then detect electron polarization. And indeed, that works. So the black line here I showed you before is just if you would detect the electrons right here and increase that length. Now we go to the maximum here, and now we increase the length of that pulse and detect the electrons after it. You see a curve that pretty much matches the inverse of the depolarization curve. So it's not very sensitive in this regard, so it's times 50, so it's maybe 1% or so of the original signal that we got in this repolarization curve, or reverse DNP, or whatever you want to call it. You can do this a little bit better. So if you use ramped amplitude novel, you get maybe 4 or 5% back. This is in fully protonated solvent. If you go into a deuterated solvent, you can get back up to 10% now here. And here, of course, the DNP goes to the protons on the trichiral radicals. Now, just some sanity checks to make sure that we are actually detecting nuclear polarization. So you can do a phase cycle here. You can phase cycle the first pulse, and then everything that basically happens in between here shouldn't really matter. Or if you generate electron polarization again, it shouldn't really matter. And another thing, you can just record a matching profile here of this first pulse, and this always matches nicely. Now I have to speed up a little bit, but what I want to give back is that I can do this after 20 milliseconds, and this is actually much, much longer than the electron T1. Something you can do, so you can just wait a little bit in between the DNP and the reverse DNP, and then you get a decay, which is the proton polarization decay of the protons that are close. If this is T1 or spin diffusion or both, well, you have to find out a little bit. But this is also nice because this is at much lower concentrations actually than for DNP. Well, I studied influence of temperature, so it's actually quite temperature independent, while the T1 is very dependent on temperature of the electrons, the T1 of the electrons. You can look at solvent deuterations. So if you use deuterated solvent, basically the signal is hardly decaying at all. And here I don't measure much longer because actually it's basically a bug in the EPR spectrometer that can solve, but nobody ever planned to take seconds between scans on an EPR spectrometer. You also see some concentration effects. So we might study something like electron-mediated spin diffusion or whatever you want to call it. You can also do electron decoupling. So if you invert the electrons periodically, you actually get a faster decay of the nuclear polarization. So here this is with 100 micromolar, the decay with 5 millimolar, and this is a logarithmic scale. And then if you invert the electron spin every 30 microseconds, this decay gets faster. And basically, why do I want to do this? So I think this could give us some information about spin diffusion processes. But as an EPR spectroscopist, what I want to do later with it is basically something like this. So really indirect detection in a way that you polarize the nuclei, you do some kind of manipulation on the nuclei, maybe even in the time domain, and then you transfer it back to electrons and detect it. And probably this will also need some smart decoupling strategies during the RF pulses. And then, I mean, this is already quite far away, I would say, but you could also get really crazy and think about, well, combining this with actual pulse sequences from solid state NMR. So I think just might give some chance about like mix and match with other concepts that are known in EPR and NMR, but it will need a few things. So I want to combine it with these improved DNP sequences that I showed you at the start. I want to try with different radicals and different nuclei, and all this has to be tested whether this actually works. Then many people I want to thank. So Gunnar, basically, he was my PhD supervisor. Matthias was my unofficial second PhD supervisor. And then many people that helped me with the setup, with the theory, the samples, etc. And I thank all of you for your attention. And I'm a bit sorry for taking a bit too long.
Okay. All right. Well, thank you very much, Nino. It was a really interesting talk. Lots of new twists and turns. It's always nice to see somebody shoving microwaves into NMR experiments. It's, so let's take a little bit of time, maybe for the questions to appear. I think there's already one question here. I've had a question. Now this guy just says wonderful talk. Okay. But if you go back to your bandwidth slide, on the
of this base.
Yeah. Right there. Yeah. Okay. So what is the dip in the center of the base experiment as opposed, and then you get a peak, sort of an asymmetry in the adiabatic base bandwidth. And then you didn't say anything about these satellite lines that are out at minus 60, 30 to 60. Maybe you did say something about them, but
but there are just quite a lot of details that I kind of skimmed over. So one is that here I swept the frequency of the pulses. And for novel and ramped amplitude novel, I basically compensated the resonator. So I could just adjust at each point here, it's the same kind of matching condition at this frequency, because there's a resonator here that maybe looks something like this, the maximum peak intensity. And for the adiabatic base, I couldn't do that just because I used the highest power that I have. So I cannot go higher at the edges. And what this dip here exactly is, that's why basically here you see, basically what you see here at the top is more or less the resonator profile actually. I mean, at least in this region here. The dip here, I'm not entirely sure. The side bands here are, I would call them modulation side bands. So because you're going XIX, basically you generate Fourier components in a way that at this offset, there's actually a resonance condition again. Does that make sense?
Yeah. Mm-hmm. Okay. Yeah. No, I mean, we've seen things like that, similar to that. Yeah. I mean, your comment about the width of the bandwidth of the experiment being much larger than the EPR line, you know, that was an interesting comment in the sense that we really have two narrow line radicals we use a lot for DNP these days. One's the tridal, which you've used. The other is BDPA. And tridal has the larger G anisotropy, so the larger bandwidth as you go up in frequency. But neither of them are actually all that broad.
Yeah, I mean, it's the narrowest EPR spectrum I ever had in my PhD.
Yeah, no, I mean, and unless you go to a nitroxide, which is now, much larger, you actually don't need this bandwidth, which is kind of strange in a way. I mean, it's an unusual situation. Now, maybe new radicals will start to show up. So let's go to the other questions, okay? So Thomas Schmidt, it's amazing, great job, Nino. It would have a great application towards DEER, as one could envision to expand the isotope labeling schemes, methyl labeling in proteins to detect and isolate multiple distance components. Did you measure any molecular motion, such as tunneling, with it at low temperatures?
No, so it's very proof of principle experiments here. But I actually haven't thought about what you just said, but I guess you could also use it as a spectroscopic filter. If you have a specific nucleus close to it and get I think you talk about the reverse DNP, that you would transfer to a nucleus and back and then make sure, okay, you only have these kind of radicals. But I haven't thought about detecting molecular motion and so forth. So I'm happy to understand this kind of spin diffusion and T1 effects that I see, which I don't quite yet. So I think, but something one could try, I guess.
Yeah, well, there are lots of cases where motions have been studied around, and you do see these methyl groups go into slow exchange at temperatures around 80 Kelvin, 100 Kelvin. So anonymous attendee says, very cool stuff. It is a surprise that we were able to match the resonance conditions as we predicted. I missed what's the purpose of doing this. Can you explain that part? I'm not sure which resonance there were lots of resonance conditions, right?
Yeah, I mean, I guess I'm not sure. I mean, here, the purpose of this is in a way that if you want to make better pulse DNP sequences, you better know what conditions you have to fill that there is actual transfer. And I think that's what I wanted to say. So so in this sense here, just by knowing it on itself is not it's not necessary, but it's similar to a way that you have to know that they are horror resonance conditions and rotational resonance conditions, and you better know where these are to understand your experiments and to plan better experiments. I guess that's the purpose of this slide, or what I wanted to show.
And then there's another question is, which one is better, Tridal or BDPA at X or Q band?
I don't know. I haven't tried BDPA.
You didn't really use BDPA, did you?
No. No.
Because you were working in aqueous media, glycerol water. Yeah. Mm-hmm. Yeah. So Alex, did you have a question? You had
a couple of the technical questions, more theoretical, brief. One is you did the separate amplitude in your transfer, your cross polarization, in order to eliminate what looked like very small fluctuations in the very beginning of your curve. Now, if those curves are not coming from electronic sources, it could be that actually expanding them and looking at them gives you a rich source of information concerning dynamics, spin dynamics that's occurring on that time scale.
So the oscillation
well-known phenomenon in the NMR case, that opening up the cross-polarization ringing, there's very fast ringing at the beginning, then slower oscillations. This is Hahn's work in the very early days. You get lots of information on the couplings and the dynamics from the early structure. Have you tried opening that up?
I think it's what you see is just the electron nutation frequency, basically. It's just not sampled very nice. But if you
if you open it up, do you see electron precession?
Well, you see electron nutation precession around the effective field, basically.
Yes,
but you know that frequency, basically. But it might still be that there's more information that I give it.
Take a look. Just open it up and just take a look at it. Is my recommendation. You can be very surprised by these short-term transients. because the rotations look pretty different. Lovely talk, by the way. For me, this was wonderful to see the solid state NMR type. Bob likes to see microwaves creeping into solid state NMR. I like to see solid state NMR creeping into the microwaves in the DNP. Your argument about the matching condition at the sideband, you've got to modulate it, in this case, X minus X. And you're making an argument about what happens at the main center band. Then you say, and at the sideband, we can treat the sideband as if it were a separate irradiation and look at the conditions there for matching. That's a kind of very dangerous argument. As you know, you're in a nonlinear regime, and doing a Fourier transform on the irradiation sequence itself and arguing about the sidebands.
So this was just a very, I think it was just a very hand-wavy thing of thinking about that they should be there somehow. But basically in the theory that I presented here, the offset is basically an explicit or an implicit parameter of the interaction frame transformation.
Okay, so for the first,
so you could actually,
for the leading term of the offset, that's valid. That's correct. Yes. For the sidebands that come from that or from higher order terms, you cannot make that argument. You've got to do the whole nonlinear transformation. Otherwise, you get this famous case of a sequence of 360-degree pulses, which have sidebands everywhere, but nothing happens anywhere. And so that's a really very, very good example of that. Thank you very much for that, Nino. Very nice talk, and thanks for answering.
Kong, do you have any?
No, it was a very good talk. I don't have much question because I talk to him too often, you know. So just if you want to think of a nicer name, of course, I named the base sequence. Maybe I've not told you this. It was actually we made the top DMP. Then I want to call it a bottom TMP, and bottom sounds too bad, so I call it base. So this is a small joke from my side. But if you are thinking for something for reverse DMP, I don't know, dynamic electron polarization, DEP, depth, or something.
When I thought about that, I recognized
could be PND. That fits the X minus X as well. It looks like it fits very well into your framework.
Yeah, you could think about it. DEP
or RMN.
Or do not publish DMP or whatever. That's Bob said this all the time. And just one more thing about the outlook. I think that's highly interesting because the outlook that you put in NMR, that's what we call a proton detected HSQC. You could call it electron detected HSQC.
Yeah, I mean that's basically the idea. I'm just not. I mean,
exactly.
I don't know exactly how feasible it is, but it looks like, at least in principle, something like this might actually be possible.
Yeah, electron detector HSQC. You get a boost of 658, blah blah blah. That's all from my side. So, but very, very nice talk.
All right, very nice talk, Nino. Thank you very much. Yeah. Okay, so the next speaker is Józef Lewandowski, and Józef was an undergrad at Amherst College, where he got a bachelor's degree in chemistry. And also, very interestingly, one in theater and dance. And we were hoping he would do maybe a dance and theater routine for us today, but he says he's going to postpone that for a while at least. Anyway, he got his PhD here in our group at MIT. He went to a very nice postdoc with Lyndon Emsley in Lyon, and following that became a professor at the University of Warwick in the UK. And he's been there, I don't know, 10 years now, almost, probably, something like that. Yep.
Exactly.
And today he's going to tell us about interacting intrinsically disordered regions and complexes in the solid state. So, Józef?
Yeah, 1 second, just share my slides. Can you see that?
Yeah, it's fine.
Excellent. So thank you, Bob, for the kind introduction and also giving me the opportunity to speak at this forum. So, I was thinking what to talk about, and we did quite a bit of methodology lately, but then I thought, I always talk about methodology. So let's talk about some applications. And in particular, I wanted to tell you a little bit about some of the sort of the good, the bad, and the ugly of looking at intrinsically disordered regions in complexes in solid state NMR, and sort of showed you, while this is quite challenging area where there's still a lot of problems, there are also lots of opportunities. And there are some things that we can learn with solid state NMR that you can